Welcome to the fourth video about discrete random variables. Last time, we defined binomial random variable as a number of successes in a series of Bernoulli trials and generated it in R. In this episode, we will calculate the probability of each outcome in the binomial distribution. We defined binomial random variable S as the sum of n IID Bernoulli trials, each with probability parameter p. We can think of each Bernoulli trial as tossing a coin, where probability of getting heads is p and tails 1 minus p, or q. We will start with calculating the probability of s equal to 0, which is equivalent to getting 0 heads in n trials. For the sum being equal to 0, all the trials must also be equal to 0. So the probability of getting 0 heads is equal to probability of getting tails in each trial. Since the trials are independent, this probability is equal to the product of the probabilities. To convince yourself that this is the case, think about probability of getting 2 tails in 2 fair coin tosses. It is equal to probability of getting tails in the first toss, so 0.5, times the probability of getting tails in the second toss, so also 0.5. It would be not true, however, when the trials were not independent. For instance, where the second coin toss has got always the same result as the first. But here, the trials are independent, so we can write them as a product. Since all the Bernoulli variables are identically distributed, these probabilities are the same, each equal to 1 minus p or q. We multiply them n times, therefore the final probability of getting 0 heads is equal to q to the power of n. Let's now calculate the probability of getting heads one time out of n trials. We can formulate it like this, using the mathematical notation. There exists exactly one trial in which we got heads. It implies that for all the remaining trials we got tails. There are several possible combinations of this event. One possibility is that we got heads only in the first trial and tails in all the remaining trials. Another possibility is that we got heads in the second trial and tails in all the remaining trials. We continue this logic till getting the heads in the last trial. These are all the possible elementary events in which we get 1 heads. The probability of each one is probability of getting heads once, which is p, multiplied by probability of getting tails n minus 1 times, which is q to the power of n minus 1. We sum all the elementary events, so we need to multiply the product by n to get to the final probability. So what is the probability for the general case when s is equal to arbitrary number k between 0 and n? let's apply the same logic. In each of the elementary events, we need to get heads k times, which has the probability of p to the power of k. We also need to get tails n minus k times, so all the remaining times. So we need to multiply our probability by q to the power of n minus k. Finally, we need to count how many possible combinations there are when we have k heads in n tosses. This is equal to number of ways we choose k elements from a set with n elements. We call this number n choose k and denote it like this. We have now the general formula for the probability of binomial random variable being equal to k. Note that if we choose k to be equal to 0 or 1, we agree with the formulas that we derived before. To get a better feeling what this n choose k means, let's calculate the sum of all the possible elementary events and see if it adds up to 1. We sum all the possible results from k equal to 0 to k equal to n. Let's substitute the probability with the derived formula. So how do we attack this problem? Let's maybe start with the case p equal to 1/2. If we substitute for p and q, which is also equal to 1/2, we see that the power of 2 adds up to n. K plus n minus k equals n. So it's no longer dependent on k, and we can take it out of this sum. So what is left in the sum? N choose k is a way of choosing k elements from a set of n elements. So each time we have the set that has got n elements, it's just the k that changes. So we add number of subsets that have 0 elements, 1 element, 2 elements, and so on, up to n elements, which is the whole set. So, in other words, we have here the number of all possible subsets of the set that has got n elements. How many subsets does a set with n element have? It is 2 to the power of n. 2 to the power of n cancels out, and our sum is 1. Okay, so for p equal to 1/2, it adds up. But what about the general case? It turns out that we can do this calculation using polynomials and so-called Pascal's triangle. Let's write down how polynomial p plus q looks like depending on the power n. On the left, we write the coefficients of the polynomial. If n equals 1, it is just p plus q. We write 1 and 1, which are the coefficients of p and q. Nothing exciting yet. If n equals 2, the coefficients of the polynomial are 1, 2, and 1. These coefficients are also respective number of subsets of a set with n equal to elements. To choose 0 is 1. There is only one way to choose 0 elements from 2. To choose 1 is 2. You can choose either the first element or the second element. To choose 2 is 1. There is only one way to choose all the elements. Let's check what happens if n equals to 3. The coefficients are now corresponding to 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Now, note how the triangle expands. Each number is the sum of two numbers above him. 2 is the sum of 1 and 1. 3 is the sum of 1 and 2. You can write it down further, and it will correspond to coefficients of higher order polynomials. What is important for our calculation is that our sum is exactly the expanded form of polynomial p plus q to the power of n. But p plus q is just 1, which proves that our formula makes sense. All the probabilities add up to 1 in general case. In the next episode, we will compare this result to the results we get from simulations in R. I hope you enjoyed that, and I will see you in the next episode.